morning, this is Dr. Ch4 Louise Liu again from Texas A&M University Kingsville, and I'm the instructor for the organic chemistry. What we are going to do today is talking about the preparation of alkyl halides. You can have different ways to produce alkyl halides. First of all, we are going to discuss the alkyl halides preparation from alcohols and hydrogen halides. And then we also discuss about different chemical mechanism. So essentially we are studying two types. One is called SN1, another one called SN2. In this reaction, we mainly focus on the substitution reaction. S represents substitution, N represents nucleophile. 1 and 2 represent the number of molecules involved in during the rate limiting step. So that's the major chemical reactions for today. So the first one about preparation of alkyl halides from alcohol and hydrogen halides. The general chemical reaction can be written down this way. You have your alcohol, you have your hydrogen halides. What you are going to do, you simply replace these halides. Replace your OH by the halides. Using your halogens to replace OH, you produce alkyl halides and produce a water. This reaction, you also need to know how many different types of reaction is going to happen. If you have different alcohols, you have primary alcohol, secondary alcohol, tertiary alcohol. What the mechanism will be for different reaction? Which one is more reactive? Generally speaking, if you have three types of alcohols, the tertiary alcohols will be more reactive. Tertiary alcohols reacted with hydrogen halides. Hydrogen halides usually follow the SN1 reaction. Primary alcohol, so it has a slower rate compared with the secondary alcohol. Tertiary alcohol has the most reactivity. So tertiary alcohol reactive much faster compared with the other ones at a lower temperature. On the other hand, so your primary reaction possibly needing higher temperature. So again, our alcohol hydrogen halides, they react to produce the alcohol halides and the water. You can have three types of different reactions: primary, secondary, and tertiary. If you have this tertiary alcohol, for example, so it's a terbutyl alcohol, tertiary alcohol reacted with your hydrogen halides, you are going to produce a tertiary chloride. So what we found, this reaction has pretty high product yield, about 78 to 88%. The temperature is at 25 Celsius. If you have a secondary alcohol, such as cyclohexanol, this cyclohexanol reacted with hydrogen bromide, you do need a higher temperature, about 80 to 100 Celsius. You simply replace this OH by the bromo. So you produce bromohydroxane, which gave you 75%. If you have a primary alcohol, this alcohol is a heptanol. This heptanol reacted with hydrogen, say bromide, at a very high temperature, 120 Celsius. You produce the 1-bromoheptane. So this reaction is reasonably with high production yield. So we want to know how this reaction occurs. If you have a tertiary alcohol, what is the mechanism for this reaction? So first of all, let's mention SN1 mechanism. SN1 mechanism usually is applicable for this tertiary alcohol which reacted with hydrogen halides to produce tertiary chloride. So again, this reaction, the following reaction, represent terbutyl alcohol reacted with hydrogen chloride. From the left, two reactants, to the right, two products. You produce a terbutyl chloride and your water. So the mechanism is going to show you how the reaction occurs step by step. So let's see. So this reaction again is followed as an one reaction mechanism. What does that mean? Meaning you are going to see three major steps called protonation, dissociation, and attachment. The first step is defined as protonation. So if you have your terbutyl alcohol and then you place this terbutyl alcohol into your hydrochloric acid, so this is two different reactants. What's going to happen? Let's see. In your HCl, your hydrogen is more positive partially charged. Your oxygen have two lone pairs, and these two lone pairs is going to attracted to the hydrogen, resulted in the bond cleavage between hydrogen and chlorine. So you form a chloride. This hydrogen is going to be bonded with your oxygen. Due to the lack of electron, make your oxygen more partially charged. So in this case, this compound called intermediate, we call it terbutyloxonium. Terbutyloxonium. This oxonium will not be stable. It's a very unstable intermediate. In this first step, protonation, you form essentially look like protonized of your alcohol. So your alcohol acts as a brownish lauryl base, and your HCl is your strong brownish lauryl acid. So brownish lauryl base alcohol has been protonated by the strong acid, and your chloride, this chloride is the conjugate base of your HCl strong brownish lauryl acid. HCl and Cl negative, they are conjugate acid base pair. And then this intermediate will subject to the further reaction. Also, you can see this first step related to the two molecules you call the bimolecular reaction. This step is reasonably fast. This step is also found to be an exothermic reaction. Again, your transient state intermediate terbutyloxonium, this is a positively charged ion. This cation ion is not stable. This cation ion and your chloride, they can tentatively form a through intermolecular forces, ion dipole intermolecular forces, to form this transient intermediate. And what happened followed by second step, dissociation will happen. This dissociation is the is the slow step. It's happening slowly, involved in the breakdown of this oxonium. So to release a water molecule and then to form a carbocation. In this step, your carbocation will be produced. What's going to happen? So this carbon-oxygen bond, these two electrons will be subject to the bond cleavage. So two electrons go to your water. Make your water have two electron lone pairs. This positively charged ion move to the carbon. You form a terbutyl cation. This terbutyl cation called carbocation. This carbocation intermediate is relatively unstable. Carbocation is not stable. Therefore, your carbocation should have a higher energy, because your central carbon has one electron, which is in lack of electron. The central carbon does not follow the octet rule. If not follow the octet rule, generally speaking, is not stable, meaning either gain one electron or something else is going to happen. If you have a positive charged carbocation, terbutyl cation, don't forget in the previous step, you produce a chloride. there's a negatively charged ion and you have a positively charged carbocation. This chloride is going to be attached to the carbocation. So positive and negative, they are reactive to each other very rapidly. You produce a terbutyl chloride. You convert alcohol to the alkyl halides. This step is considered the Lewis acid-Lewis base reaction. Your chloride, negatively charged chloride, donate 2 electrons to the carbon. They form a bond. So this chloride is also called nucleophile. Love's nuclei is the nuclei seeker. This reaction involved in 2 molecules is called bimolecular reaction. This reaction was also found to be an exothermic reaction. So generally speaking, the last step, the third step, is considered attachment between chloride, nucleophile, and carbocation. This reaction involved in 2 molecules is a rapid step. So that's the general speaking about 3 steps. First one, protonation. Second one, dissociation. Third step, attachment. Through 3 steps, you form a alcohol halides by using alcohol and hydrogen halides as reactants. In terms of your carbocations, we need to understand what's the carbon orbital hybridization. Is this carbon positively charged or negatively charged? So carbocation 6 nuclei or 6 electrons. Is a carbocation acting as a Lewis acid or Lewis base? That's our question. Let's see. First of all, your carbon was found to take the carbon in carbocation is found to take sp2 hybridization, meaning this carbon 1 positively charged in the middle, 2, 3, and 4. They are going to form a trigonal planar structure. So your carbon has been positively charged. So carbocation meaning positively charged, meaning in one of the p orbital you don't have the electrons. Positively charged carbon in the p orbital, which is empty. Carbocation, because you have a less electron, so therefore carbocation is going to seek electron. You call it electrophile, loving electrons, because you need to accept electrons. So therefore you call this carbocation as Lewis acid. Remember AA, acid accepts electrons. So that's essentially about the carbocation, the natures. To summarize this reaction SN1 reaction, to summarize it, point 1, the sum of each step in the reaction mechanism must be the same, must equal the overall reaction equation. You're adding different steps together. That reaction must be the same as your overall reaction equation. In your reaction, because you have a substitution reaction occurs, so when the chloride nucleophile takes place of your OH, so that reaction is nucleophilic reaction. So you consider the N, you call substitution represented by S, nucleophile represented by N. And then your slow step is your second step about that carbocation formation. So the second step is involved in only 1 molecule. You call it unimolecular reaction in your step 2. So this step we found is slow. This slow step is determined as the rate determining step. Second step determining rate step. And the overall reaction cannot go faster than this rate determining step. Therefore, the total reaction is called SN1. S again represents substitution, N represents nucleophilic, 1 represents the rate determining step involves in only 1 molecule. It's a unimolecular reaction. In this case, is your step 2. So this is about the SN1 reaction. So let's moving on to the structure, bonding, stabilities of carbocation. As we mentioned, your carbocation has 3 key natures. Number 1, carbon in the center of your carbocation takes sp2 hybridization. So which meaning this carbocation usually is a trigonal planar structure. So the positively charged carbon represent an empty p orbital. Carbocation, due to its nature, lack of electrons, carbocation is known as an electrophile. It's also acting as the Lewis acid. So let's see the stability of these carbocations. So as we mentioned, you can have a methyl cation, you can have your primary cation, you can have your secondary cation, you can have your tertiary cation. Which cation is more stable? So you consider this way, you have a positive charge. If this positive charge can be delocalized, meaning if this positively charged carbon can be connected to some other carbons, your cation carbocation will be stabilized. Which carbon is going to be connected to more other carbons? So this tertiary carbocation. So this carbon connected to 3 other carbons. Therefore, you call it, you consider this tertiary carbocation is more stable. Even though we said more stable, doesn't mean it's stable compared with the neutral molecule. Because you have positive charge, you don't follow the octet rule. Carbon does not follow the octet rule, meaning even though we said this is stable, but again, it's still intermediate. It's going to convert to something else. So stabilization of your carbocation, so generally speaking, due to the delocalization of your electron. So imagine you have carbon 1, 2, 3. This carbon you call alpha carbon, the other one called beta, and then gamma carbon. So this alpha carbon can be the sigma bond from your alpha, your alpha carbon is a carbocation, your sigma bond from your beta carbon can help you to delocalize your electrons. Therefore, your stability for that carbon will be further increased. So again, your carbocation, which with the tertiary case is more stabilized. If you want to learn a little more, you can go back to study the valence bond model. Valence bond model which shows the orbital overlap. Your molecular theory, your molecular orbital theory can help you to predict the bonding orbital with the electrons which can form the sigma bond. So again, let's continue our lecture related to the stability of carbocation. Again, the more decolorized your electrons, so the more stable the related carbocation is. You can use a valence bond model to show the orbital overlap. Molecular orbital theory can help you to understand or predict the 2 electrons which can be spanning over the sigma bond and over this beta carbons. So and then we are going to further study the effect of the alkyl structure on the reaction rate. So as we already mentioned, so you form in the rate step, determining step, you are forming an alkyl oxonium ion. This alkyl oxonium ion is going to subject to a transition state, as what we showed. In this transition state, your carbon-oxygen bond will be start weakening, meaning your oxygen, this positively charged ion, is going to attract to more electrons. Carbon becomes more positive, oxygen becomes less positive, and then this bond completely break up, oxygen uptake to electrons. So take 2 more electrons becomes water, and then your carbon-oxygen bond completely cleavaged. You form a carbocation. This carbocation formation rate is proportional to the concentration of this oxonium, alkyl oxonium cations. And then the rate of your formation of your carbocation also related to the stability of your carbocation which formed. As we mentioned, you have tertiary carbocation, that transient state is more stable. So in that case, you have less energy, and then you can go to secondary, primary, and go to methyl carbocation. Again, you can also use the activation energy to track the stability of your carbocation. To summarize it, to simplify it, your tertiary carbocation is more reactive. The reaction rate, generally speaking, also going to be increased accordingly. Definitely, the other carbon-carbon existing, the carbon chain length also affected on the carbocation formation. And then what's the chemical reaction for your methyl or primary alcohols? If you have primary alcohols, you form a less stable carbocation, primary carbocation. What's going to happen in this case? Let's take a look of this reaction. If we have one pentanol reacted with hydrogen bromide, you simply replace this OH by Br. You form one bromoheptane and water. So this reaction is going to go through the reaction we call SN2 mechanism. So what happened? Let's take a look. This SN2 mechanism involved in 2 steps. One step is called protonation, proton transfer. Similar to your SN1, you must form a cation. You must form something we call the oxonium, positively charged oxygen, which is not stable. Oxonium must be formed. And then the second step called nucleophilic displacement. In this SN2, you only have 2 steps. The first step, protonation. The second step is displacement. Displacement is going to be involved in 2 molecules that reaction rate is slower. That's the rate determining step. So let's again take a look at our molecule. You have oxygen, hydrogen. So your oxygen have 2 lone pairs. So the lone pair is going to attracted to the hydrogen from your hydrogen bromide. Therefore, hydrogen bromide, that bond is going to be cleavage, the subject to the hydrolytic bond cleavage. Your bromine becomes to bromide negatively charged ion, and this part, this heptanol, becomes heptooxonium. And this oxonium, as we mentioned, so is not very stable. It's going to further produce a primary carbocation. So this primary carbocation, if you form a primary carbocation, let me come back. This carbon will be positively charged. Due to the stability issue of this primary carbocation, what you are going to see, you are not going to form the carbocation. Instead, you are going to attract, your nucleophile bromide is going to directly attracted to this carbon, which connected to this OH2. So what's going to happen? You are going to see a nucleophilic displacement because your bromide is much negative. So this carbon-oxygen bond is going to be loosened up. So 2 electrons completely accepted by the oxygen form this water, and then your Br negative completely reacted, bonded with your carbon. This is called the displacement, nucleophilic displacement, because you have 2 species involved in, so 2 molecules involved in. That slower step is called bimolecular reaction. Bimolecular reaction. Therefore, This mechanism, you consider it as SN2. You have two steps, protonation or proton transfer and nucleophilic displacement. This SN2 is more commonly applicable for your primary alcohol. How about secondary? Secondary alcohol, sometimes you are going to have possibly two different types of reaction mechanism. Both could be reasonable. That one will be highly depends on the individual reactions. In order to produce different alcohol halides, we can also use other two special reactions. This reaction is from converting alcohol to alcohol halide using thiol chloride. If you have SOCl2, thionyl chloride is a very good reactant. It's going to react it with your alcohol, primary, secondary, tertiary, whatever the alcohol you have. So normally people using the alcohol which is primary alcohol or secondary. But anyway, tertiary, you can also use this reaction. So this OH will be replaced by one of the Cl. You produce alcohol halides and sulfur dioxide and hydrogen chloride. In this reaction, you use a pyridine so to neutralize the HCl produced. HCl is a base, the pyridine is a weak, HCl is a strong acid, and the pyridine is a base. So you use this pyridine as your solvent also to neutralize your strong acid you produced. So that's essentially about another reaction to convert alcohol to alcohol halides through thionyl chloride, SOCl2. The third reaction convert alcohol to alcohol halides using phosphorus tribromide, PBr3. This PBr3 again reacted with your alcohol. So phosphorus tribromide reacted with alcohol. So you produce 3 moles of this this RBr, so alcohol bromide in this case, and then you produce a phosphorus acid. For example, if you have this alcohol, you simply replace this OH by the Br. Because you have 3 Brs, you can balance it by 3 moles and 3 moles. Similarly, if you have cycloalcohol, you'll simply replace OH by the Br. So this is a very clean reaction. And the fourth chemical reaction to convert the compounds to alcohol halides is using the halogenation of alkane. Halogenation reaction with the alkane, so RH, alkane reacted with halogens to produce alcohol halides. This halogen can be fluoro, chloro, bromo, aldo. To emphasize, this fluorine reaction is actually explosive. So in this case, we normally don't use this reaction to produce halides. And then your iodine, for the iodine reaction is endothermic. So you have to keep input the energy or heat it up. This is not feasible for us to use. So commonly used one will be chloride and bromide, chlorine and bromine. So these two reactions, they both exothermic. The reaction rate is controllable. You call them chlorination and bromination. So a little bit later, we start your lecture 3 over chapter 4. So let's call it a day today, and you stay safe, stay happy. Thank you so very much. Goodbye.